Okay, so I said I'm going to move on to the mixed statements, but before that, I want to talk about the negation. Okay. Oh my gosh. Let me talk about the negation. Okay, so the first thing is how should we negate AND statement? What is not P and Q? Which means, what does it mean that P and Q is false? So P and Q means that both of them are true. If that is false, then it's equivalent to say at least one of them is false, right? If not both of them is true, then at least one of them is false. It's equivalent, which means this is true, which means this not P and Q is equivalent, logically equivalent to not P or not Q. This is called De Morgan's law. And also together with another one, which is not P or Q is equivalent to not P and not Q. Okay? Which means you can think of this as something similar to distributive law, like you just put the not into P and into Q, but you have to change and the logic and into logic or, and you have to change logic or into logic and. Okay? So this is De Morgan's law. Okay, so this is and also you have, if you take not of P, then this is clearly logically equivalent to P, because not is itself, right? True becomes false and then becomes true, and then false becomes true and then becomes false. So this is double negation. Okay, and what I want to talk about today is what is the not of for all x in a P of x. So this means P of x is true for all x in A. If this is false, then it is equivalent to P of x is false for some x in A, or for at least one of the elements in A. So then this is equivalent to say there exists some x in A such that this is false, not Px, right? So what's happening here? If you want to take the negation of a for all statement, you change it into a there exists statement, and then you negate the statement after the quantifier. Okay? And this is very interesting because if you look at the not of there exists, then the same thing happens. So this means some P of x is true. If this is false, then it means it means it's equivalent to say every P of x is false, right? So this means for all x in A, you have not P of x. You have not Px. Which means if you want to negate a there exists statement, you change the quantifier into for all, and then you change the P of x into not P of x. Let me share one more example. What if we have for all? What if we have for all x in A, there exists y in B such that P of x y. Okay. If we want to show this is false, what would be the statement? How should we simplify? Okay, then this will becomes. So we can think about this as the entire statement about x. Okay, we can call this Q of x. So then so by the first criterion, this will becomes there exists some x in A such that not Q of x, right? Such a not Q of x. And then this Q of x is also in the quantifier, it's there exists, so that this will becomes, so by the second criterion, this is for all y in B, we have not P of x, y. So if we look at the original statement, it is for all there exists P. And now it becomes there exists for all not P. So this means we don't actually need this intermediate step. All we need to do is swap or flip or switch all the quantifiers and then put a negation to the last one. Okay, so for example, if we have for all x, for all y, let me just quickly, let me just put quickly in this way. If we want to take the negation, then this is going to be there exists for all, there exists p. Okay, sorry, not p. It has to be not p in the last one. In the last one. And we also need to know one more thing that is the most important, that most students make mistakes, or students make most mistakes. That is when you take the not of p implies q. I have mentioned that this is actually clearly equivalent to p does not imply q. And I have actually defined that this is true if and only if p is true and q is not true. So what it means is that this is actually logically equivalent to p and not q, right? P and not q. So let me show you an example. So just some random thing. So if we want to negate x in A, implies x is bigger than 2. By the way, this means all elements in A is bigger than 2. If you want to negate this, then this x is in A, but and this x is less than or equal to 2. Does it make sense? This is very important. This is extremely important. I mean, students make a lot of mistakes here. If you want to negate something, p implies q, it means p is true and q is false. It is quite asymmetric, right? It's not symmetric because here it's the same, but here it's not. And the reason for that is really hidden, like in the definition of not implies. Because just imagine what it means that a statement does not imply the other statement. This will only happen if the first is true and the second is false. It means the fact that the first statement is true cannot imply the second one is true, right? So this only happens when this is true and this is false. So if you just think about it in this way, then you can memorize that not p implies q is equivalent to p and not q. Okay, which means if you want to negate some statement like this, if you want to negate, for example, x not x in A, and if you want to negate for all x in A, p of x implies q of x. Here, p of x is a statement about x, and q of x is also a statement about x. Then this will be there exists some x in A such that p of x is true, but q of x is false. Okay, so this is the real statement. So let me show you an example. So which means if you want to show this for all statement is false, then all you need to show is that this is true. Okay, so this is proof by negation. This is called proof by negation. This is not so this is kind of weird because, so let me show you. If you want to show that p is false, all you need to show is that not p is true. It is kind of weird because it looks the same, but in practice it makes sense. So for example, let me show this. So this is clearly a false statement for all x in R, x is less than 100. This is clearly false, right? Because this means every real number is less than 100. Clearly, all the you have a lot of you have infinitely many real numbers that are at least 100. This is false. So we're not asking to prove it, but we're asking to disprove it, which means we want to prove that this is false. So to prove it by negation, all we need to show is that the negation is true, which means all we need to show is that we can find some x in R such that x is bigger than or equal to 100, right? And to prove it, we can just take x to be 101, or just simply 100. Take x to be 100. Then this is bigger than or equal to 100. So the negation is true, which means this is false, okay? So this is a disproof of the original statement. Also, let me show you. So I will not give an example, but I will just tell you how to disprove. Like for x in A, P of x implies Q of x. Okay. So to prove it, all you need to show is that you can find some x in A. So you want to negate implication. All you need to do is you want to find some x in A such that P of x is true and Q of x is false. Just keep that in mind. You will meet it infinitely many times. This is very important. Okay, so now I will talk about the mixed statements and then how to prove or disprove some mixed statement. By the way, I have shown that to disprove any statement, all you need to do is just to prove the negation, right? And then every negation is also in this form, right? It consists of logic and, logic or, logic not, and then there exists, and then for all, and then implies, and then equivalent, right? Every statement can be written using some symbols, letters, together with these logic signs. Some are quantifiers, some are logic operations. And if you take a negation of these things, you still get something similar. Still something can be written in these forms, right? Which means, in order to know how to prove or disprove all the mixed statements, all we need to know is just how to prove the mixed statements, right? Because you can change every question of disproving a statement into proving its negation. So that's why it's important that we talk about the negation of a statement. So let me show you. I mean, I have already told you all the tricks that you can use for the statement. So this is actually, you can think of it as a practice. All the questions are practice problems. So the first classic question is that you can show. Okay, I'll just give you some random statements, and some of them is true, some of them is false. I will deliberately give you some false ones, also some true ones, and I'll ask you to see if they are correct. Okay, so the first one is for all, and let's say for all x in R, you can find some y in R, such that y is bigger than x. Is it correct? Okay, so first we have to understand what it means. It means for all real numbers of x, we can find some y, also some real numbers, such that it is bigger than x. Which means for all real numbers, we can still find some bigger real numbers. Is that correct? It is correct. Okay, so we prove it is true. We just let x in R. And then we take any y that is slightly bigger. We can just take y to be x plus 1. So then it is bigger than x, right? It is a special value, but this special value depends on x. It's okay because this y is defined after x. So y can be dependent on x, right? Because this statement is a statement on x. After you let x in R, this x is a fixed number, which means you can use this x. You can introduce this x in the definition of y, okay? After you pick, maybe you can just say, you can call it y naught, but it doesn't matter. Then you win, okay? But if you change it slightly, then it will be false. So what about, there exists some element x, such as for all y in R, you have y is less than x, or y is bigger than x. Just change, okay? Is it possible to find some real number x such that for all y, for all real number, it is bigger than that element? Clearly not. Because, for example, you can just choose y to be itself, to be x itself. Then it cannot be bigger than itself, right? So now you want to disprove it. So I will show you a proof by contradiction. It's always better, okay? By contradiction. Assume this is true. And now let's find out. So if this is true, then it means we can take some x naught, right? Because there exists statement is true, so which means we can find some special value. Let's say we can take some x naught in R, such that for all y in R, we have y is bigger than x naught. This is true for all y. Why not take y? So we can choose. We can here it's take, because we want to deduce a contradiction. So we find a particular value to find a contradiction. We just take y to be x naught itself. Then it says x naught is bigger than x naught. It's clearly false, right? Which means this is not true. Which means this is false. Okay, so this is proved by contradiction. Does that make sense? We assume it is false, and we want to see what will happen. We assume we want to disprove this. We want to disprove this. So now we assume this is true, right? If we want to prove something, we assume the negation of that is true. But here we just assume we want to disprove this statement. So we just assume this is true. If this is true, then we can take some special value x naught, such that this is true. Such that for all y, for all real numbers, it is bigger than x naught. But then we can just choose y to be itself. Okay, so here it's kind of tricky, but we can actually change it into x, y bigger than or equal to x. Then here we cannot choose x naught, right? Then we have to be more careful, but not too careful. Even if it's bigger than or equal to, it's still false, because we can just simply take y to be any value that is less than x naught. We can just take y to be x naught minus 1, and we win, because we can take any value, right? This is a very strong condition. We take y to be x naught minus 1, then x naught minus 1, it should be less than x naught, but it's also bigger than or equal to x naught, so this will also lead to a contradiction. So this is, I always prefer proof by contradiction. I think it's always more straightforward. Otherwise you have to prove its negation, right? So otherwise it's kind of a direct proof in the sense that you prove it directly, but you have to use negation. Because using negation in this case is the only way is the only direct proof. Okay, so prove by negation. If you want to disprove that, then clearly you can prove it by you can disprove it by proving its negation is true. So all you need to show is for all x in R, you can find some y in R such that y is less than x, right? So then you want to show this is true. So you can see it's exactly the same thing, right? So the main idea is the same. So why not use proof by contradiction? I understand for beginners, it is much easier to prove by directly to first use negation and then change it into a problem that you can use direct proof. But the idea is that you can only become more mature in math or more familiar with math or logic or quantifiers or statements or proof methods by really practicing a lot, especially on those methods that others are not that familiar with. For example, proof by contradiction. Okay, so you have to be familiar with that. And then you can choose whatever you want that will make the proof shorter and simpler. Then you have a choice. Otherwise, if you only have one method, then sometimes you just cannot, maybe you just make some mistakes, or you cannot move on, you cannot prove it quite quickly. But if you have different methods, then you can choose which is the best one. Okay. So now if we want to prove directly by negation, then just let x in R and then take y to be some value less than x. Then we just take y to be x minus 1. Okay, we win. It's trivial, but you need to switch the quantifiers, which takes time. Okay, it depends. You will choose which one suits you better, but I really recommend that all of you just get familiar with different methods, especially proof by contradiction. It's not hard. It's always better. I claim that it's always better, but sometimes it's not. Okay. So now let me show you some other examples. Okay, show for x in n natural numbers, you can find some y in natural numbers such that y is bigger than x squared plus x plus 1. Okay, let x in n take y to be slightly bigger, then why not take x squared plus x plus 100? You win. Okay. Now I have a smart example. Okay, so I'll just tell you it is true. Okay, now I want you to show that for all x in R, x is at most 1, which means it is less than or equal to 1. If and only if for all epsilon bigger than 0, for all positive number, let's call it epsilon, we have x is less than 1 plus epsilon. Okay, so we'll just see what these two statements mean. So the first statement is quite straightforward. It means this x is some number that in this interval, right? From negative infinity to 1, including 1. And we will see what this statement means. So first, we'll choose some epsilon. Let's say epsilon is 0.1. Okay, so this is 1.1. So this means x is less than 1.1. But this is true for all epsilon. So this is also less than 1. So for example, so the reason why I choose 1.1 instead of 10 or 100 is that this is actually a statement about small enough epsilon. Okay, so because, for example, this is less than 1 plus 10, but then this condition is actually strengthened into x is less than 1.1, right? Because if it is less than 1.1, then clearly it is less than 1. It's clearly less than 10. So okay, so if this is true, then it's less than 1.1, but also it's less than 1.11. So then you can see it becomes 1.01. 1.01. It's less than 1.0, but also it's less than 1.001. So which means, if you look at the set of all the x, then this actually corresponds to the intersection of all the intervals, negative infinity, all the open intervals from negative infinity to 1 plus epsilon, where epsilon is a positive number. But maybe for some beginners, it makes the question even more complicated. But it just means you're actually taking all these open intervals together. You're taking all the intersection of them, and then I claim that this set is just the half open, half closed interval from negative infinity to 1. Because you can see, however, this epsilon is small, it still need to be positive, which means this 1 is contained in any set, right? And then clearly everything less than 1 is in the set, so which means it must be, so this must be within the set. And also I claim this is exactly the set, which means if you just go a little bit to the right of 1, so let's say you go from 1 to some 1 plus delta, then you can just kill this element by considering 1 plus delta over 2, because this has to be in this interval, right? So this must be outside, right? Because you always have gaps between real numbers, so you can just always find some delta 1 plus delta over 2 to kill it. So that's the main idea why this is true. By the way, this is actually a proof that this is equal, so this is actually a proof of that. But let's assume that we are not allowed to use the methods from set theory, or it's kind of a real analysis, but let's just prove it directly, okay? Prove it directly. So first, I claim that one of these directions is trivial. Okay, so which one is trivial? I claim that this direction is trivial. So first, we have to fix some x in R, okay? Then we just want to show this is true. So I claim that the first direction is true. Okay, so the first direction is that we assume x is less than or equal to 1. And then we want to show that for all epsilon bigger than 0, we have x is less than 1 plus epsilon. But it's clearly true, because we just take or let epsilon be bigger than 0, and then x is less than or equal to 1, and 1 is less than 1 plus epsilon, right? This is clearly true. So if we have an inequality where at least one of them is strict, then the entire inequality is strict in the sense that x is strictly less than 1 plus epsilon. And we are done. So this direction is trivial. And then for the other direction, we assume that for all epsilon bigger than 0, we have that x is less than 1 plus epsilon. And then we want to show that x is less than or equal to 1. Okay, how to show? Then I claim that it's definitely better to just use proof by contradiction. Okay, we assume x is bigger than 1. And then if we can deduce some contradiction, then we win. Okay, so let's assume that, x should be less than or equal to 1. So if it is big, then it's bad. Okay, it should cause some problem. So if x is bigger than 1, then we know that x must be less than or the 1 plus something, 1 plus some small number. Then all we need to choose is we just need to choose some epsilon that is small, and such that 1 plus epsilon is within 1 and x. So the best choice is we just choose, or we take this epsilon to be epsilon is the distance from 1 to 1 plus epsilon. We want this to be less than the difference from 1 to x, which is x minus 1. So we can just take epsilon to be 1/2 of x minus 1, or x minus 1 over 2, because x is bigger than 1. So this is positive, okay? And then by this construction, you can see 1 plus epsilon is the midpoint. 1 plus epsilon is the middle point, or the midpoint of 1 and x. So it must be less than x, right? So 1 plus epsilon must be less than x. But also, by this assumption, for all epsilon, x must be less than 1 plus epsilon. So this will lead to a contradiction, which means x must be less than or equal to 1. Okay? So I claim that this is the better way. So you might, what if you want to think about some other way? Okay, so here, the thing is that you want to show that for all epsilon bigger than 0, 1, x is less than 1 plus epsilon is equivalent here you just want to show it implies, right? You just want to show the other direction. You want to show it implies x is less than or equal to 1. So if you don't want to use proof by contradiction, then you will need to consider the proof by contrapositive, right? As I said, it's basically the same idea, because every proof by contrapositive can be proved by proof by contradiction. So here, proof by contrapositive, all you need to show is that if x is bigger than 1, then you can find some epsilon bigger than 0 such that x is bigger than or equal to 1 plus epsilon. And then you realize this is exactly the same thing, because now you assume x is bigger than 1. See? It's the same thing. And then you want to find some epsilon such that this is true. So then now you assume that x is bigger than 1. So you want to show you can find some epsilon small enough such that x is bigger than or equal to 1 plus epsilon. But how can you choose this epsilon? So here you can see you can just choose epsilon to be x minus 1. So this indicates that here we can also just choose epsilon to be x minus 1, because so then this will be less than or equal to, and then this will already cause a problem. But usually we just choose it to be over 2. Okay, it will be always correct if we don't divide by 2. Then if this is this, then if this is equal and this is equal, then we cannot conclude. So it is always better to just divide by 2. Okay, I mean, we don't care, we don't need the best choice. Okay, for the there exists statement, we just want to find some value. We want to find some epsilon that is small. So if it is small enough, then it is okay that it is smaller. Okay, we choose smaller epsilon, but it definitely is unnecessary just to choose over 3 or over 100. Then it is too much. Over 2 is enough. Okay, so but here you can see, if you put it in this way, then it's trivial that you can just choose epsilon to be x minus 1 and you win, because so then 1 plus epsilon is going to be simply x. So x is bigger than or equal to x, and you win. Okay, so you can see it's actually the same thing. It just proved by contrapositive. I mean, in this case, it reduces to proof by contradiction. It's actually the same idea. So it indicates that it's not too hard to understand proof by contradiction. Okay, and let me give you some, maybe just one more example. So I want to show, so first we are given a subset A in R, and we want to show that there exists some m bigger than 0 such that for all a in A we have A is less than m, will imply that there exists some m in 0 such that for all a in A we have A is less than or equal to m. Actually, this is equivalent. So they are equivalent. So this means every element in A is less than this number m, and this means every element in A is less than or equal to m, and they're actually equivalent, which means, so here this m is considered as something called an upper bound. Upper bound means it is bigger than or equal to everything. So this exercise basically tells you that when we want to define an upper bound, it actually doesn't matter so much when this is less than or equal to, but when it comes to the least upper bound, then we have to be careful. So in practice, we call this an upper bound for a particular real analytic reason. I mean, it means a reason that is important in real analysis, or simply analysis, or mathematical analysis. But here, let's just forget about it. It just basically means if everything can be less than something, then everything is less than or equal to something, and vice versa. If everything is less than or equal to something, then everything is less than something. So here, clearly, as I said, one of them must be trivial. Which one is trivial? So this one is trivial. So this direction is trivial. Because the point, the hint, or the idea is that a less than b, it actually implies a is less than or equal to b. Why? Because this is a less than b or a equals b. So you assume this is true, and then this is a or statement, and one of them is true, and so you win. But the other direction is false. Okay? For example, if a is equal to b, then I'm claiming that this does not imply that a is less than b, because you can sometimes a is equal to b, then a is not less than b. Okay, so the other way is false, but this is true, which means you can just take the same m and you win. Okay, so if you want to write the proof, then you assume the first one is correct. So you can assume that there exists some m beginning 0 such that for all a in a, you will have a is less than m. So this means we can take some m naught, or just take some m naught, okay? Beginning 0 such that for all a in a, we have a is less than m naught. And then now we want to show that this is true. So we take m to be the same m naught. Okay, it's still beginning 0 for sure. And then we want to show that for all a in a, we have a is less than or equal to m naught. So we simply let any a in a, and then by this assumption, you can call it star. So you can say by star, we have a is less than m naught. And we want to show a is less than or equal to m naught. But as I said, by the hint, a less than m naught implies that a is less than or equal to m naught, because this is or, okay? And we win. So this is a trivial part, but this is not trivial, because in this direction, you cannot choose the same m naught, because you can just, if you want to do it, then you choose the m naught, and then you assume this is true. So here you take the same m naught, and then you let a in a, and then you have a is less than or equal to m. But this will not imply that, because sometimes a is equal to m, then a is not less than m. But you can just solve this problem by taking this m to be just slightly bigger. Okay, just to be slightly bigger. So for example, if everything is less than or equal to 3, then clearly everything is less than 4. Does that make sense? Because 3 is less than 4. So you just take this m, and you don't need to be m plus 1. I mean, you can take it to be m plus 1, but you can just take it to be m plus any small epsilon, like 0.01. It will suffice. Okay? But for simplicity, we usually just choose the, here, if it's m naught, then we just choose it to be m naught plus 1. Okay? So in this direction, we assume that this is true. So there is some m beginning 0, such that for a in a, we have a is less than or equal to m naught, or equal to m. So then we can just take some m naught beginning 0, such that this is true, such that for a in a, we have a is less than or equal to m naught. And then we want to show that we can find some m in 0, such that some m beginning 0, such that for a in a, we have a is less than m. As I said, we cannot choose m to be m naught itself, because less than or equal to does not imply less than. But we can choose m to be slightly bigger. So we take m to be m naught plus 1, which is, because this is positive, so this is also positive for sure. And then we just let any a in a, and then we want to show that this is true. But because a is in a, and then by this assumption, let's call it star. So you can say by star, a in a will imply that a is less than or equal to m naught, which is less than m naught plus 1, which is equal to m. This is a inequality where one of them is strict. So then the entire inequality is strict. So a is less than m. And you write down. Okay? So this idea is quite interesting in the sense that these two things are not equivalent, but when you add there exists, they become equivalent. Okay? It's very interesting. And you will see it infinitely many times. So for example, you can also change the thing here. You can change this into there exists some natural number. So if you can change it into you can find some natural number such that for all a is less than this natural number, and this will also be equivalent to this. So this is positive real number. We can change it into natural number, and also you can change this to natural number, and also you can change this into less than or equal to. And you can see all of them, 4 of them are all equivalent, pairwise equivalent. All of them are equivalent. So which means it doesn't quite matter if it's equal or the set is. The point is that if it is bounded above or not, okay? So all these definitions are equivalent and they are called A is bounded above. Which means geometrically, it means for all the big values, it's not in A, which means starting from some values, all the real numbers are not in A, okay? Or it means every value is less than some real number, or less than or equal to some real number, or less than some natural number, or less than or equal to some natural number. All of them are the same. You can just prove it as exercise or just for fun, okay? I mean, it's not hard at all. Just play with the tricks. I mean, maybe if you want to prove it with the equivalence with the natural numbers, you have to be careful. For example, you can prove it to be less than 3.4, then it's less than 4. What is this for? It is called the ceiling of that. The ceiling function is the or the ceiling of that. It is equal to 4. But in practice, sometimes you will need to consider the ceiling plus 1, so that it has to be bigger, and also it is also a natural number. Okay, the ceiling function. Let me quickly introduce. It's not hard. So the ceiling function. So for any real number, let's say 3.4, then if you consider all the integers that are bigger than or equal to 3.4, then they are 4, 5, 6, right? These are exactly the integers that are bigger than or equal to 3.4, and this is the smallest one. So this is by definition the smallest integer n, such that n is bigger than or equal to bigger than or equal to a in general. And then similarly, we can define. So clearly, if this is the smallest one, such that this is true, then this is clearly true that this is bigger than or equal to that. So this is bigger than or equal to a, and also this is by definition an integer. Okay, z is the set of all integers, and also you can define. So this is the ceiling function. You can also define a floor function. It is, then you just consider the other way around. It's the largest integer that is less than or equal to a. So for example, when it comes to a 3.4, then the floor of it will be just 3. Or it's also called the integral part. The floor function is also called the integral part. I mean, floor is equal to integral part, because when it comes to the positive numbers, for example 3.7, then the integral part is 3, and then what's remained is 0.7, right? It is called the fractional part, and it's denoted by the curly bracket of 3.7. So which means you define the curly bracket of a as a minus the floor of a, or a minus the integral part of a. So then this must be between 0 and 1. Strictly, this is bigger than or equal to 0 and strictly less than 1. So for example, if a is 3.7, then the integral part is 3. and then the fractional part is 0.7. And if it's negative, you have to be careful. Then the integral part is -4, because -4 is less than that, but -3 is bigger than that, right? Then by definition, this has to be -4, and then the fractional part would be 0.3. It's still non-negative, right? It's bigger than or equal to 0 and less than 1. Okay. Okay, so that's about everything. So I think I have discussed a lot of things, and in the next video I think I will move on to limits. Okay, see you in the next